Hello, my name is Yu Fu, and I will be talking to you about magnetic braking with Faraday, which is Lab 5 for Physics 2212. Introduction and purpose. Faraday's law tells us that a time-varying magnetic field creates a curly electric field and EMF. This EMF then results in a current that generates a magnetic field that exerts a force opposite to the external magnetic field. In this lab, we'll explore this concept with a falling bar magnet as our varying external magnetic field, and that the current will be induced inside an aluminum foil, which the magnet will be falling through. And we will find that the induced magnetic field creates a force that slows down the magnet as it opposes the change in magnetic field caused by the falling motion. Data and observations. Alright, we're going to play this video. The magnet falls slower in this video as it normally does in free fall, and by analyzing this video, we can determine that the magnet takes 0.9 seconds to fall through the tube. Now that we have collected empirical data, we will move on to the coding section. In this lab, we break the foil tube down into a series of thin rings to simulate the interactions between the foil tube and the magnet. The code uses the magnetic field function and the magnetic dipole calculated value from Lab 3 to determine the induced magnetic field and magnetic force. A new function is written to calculate flux. Then we take these three functions and put them in the main loop, which calculates the resultant velocity of the magnet with respect to time and then graphs it. Here's the output graph from the program. You can see it's a velocity versus time chart. And then on the right, you can find a screenshot of the program as it is running with the more brightly colored sections representing a higher current, and the different colors represent different directions of the current, either counterclockwise or clockwise. Discussion. Why can't we use a Ferris tube? The magnet is attracted to iron, so putting it in a Ferris tube would just have it stick to the side, and we wouldn't have any falling motion. What if the resistivity was reduced as far as possible to 0? The EMF generated by the moving magnet stays the same, and because I equals V over R, the induced magnetic field would increase, and thus the magnet falls slower because the resistive force is higher. What if holes or slots were cut into the tube? Holes would decrease the effectiveness of the tube to conduct the induced current, and therefore reduce the induced magnetic field, so the magnet should fall faster. If a slot is cut through the tube, no loop forms inside the tube, so there is no current, and therefore no magnetic force, so the magnet just follows as it normally would. Conclusion. We recorded the time it took a magnet to travel through an aluminum foil tube to demonstrate the resistance due to an induced electric field. Then we created a program to determine how long the calculated time to travel through the tube is using the known characteristics of the magnet and the aluminum foil tube. The values of travel time are 0.9 seconds experimental and 0.879 seconds simulated, which gives us a percent difference of 2.36%. This is really good experimental accuracy, but if we did want to improve it, we could use photo gates rather than a smartphone, which would allow us to know exactly when the magnet enters and exits the tube instead of trying to figure it out from a picture. There is a significantly slower velocity for the magnet in the tube than in free fall, and because if it was in free fall, it only takes 0.25 seconds. So we know that the tube actually slows down the magnet a significant amount, and that is because of the induced current that we observed in this lab.